Welcome to your electrochemistry experimental video. Today we will be investigating how cell potentials change with varying reagent concentrations. You will later discover how to use this information to find equilibrium constants for a reaction. To start, we need to make our reaction cell. As we need to know the exact concentration of each of our reagents throughout the experiment, we will use volumetric glassware to make our solutions. Carefully pipette 1 milliliter of iron chloride into the 100 milliliter volumetric flask. Remember that pipettes are calibrated to release the measured volume on their own. This means that we do not force the liquid out of the pipette. To complete this solution, fill the volumetric flask just to the line with water. We want to be extra careful not to overfill the volumetric flask, or we will no longer know what the concentration of the solution is and will have to remake it. Place parafilm over the top of the flask, making sure that it is well sealed. Thoroughly mix the solution by inverting the volumetric flask several times before pouring it into the reaction beaker. Next, we need to make a dilute solution of the iron 2 compound. This will be used to vary the relative concentrations of the iron 2 and iron 3 compounds in the reaction beaker. Having cleaned the glassware, the same volumetric flask will be used to make this solution as was used for the first. Following the same procedure as before, carefully pipette 1 milliliter of iron ammonium sulfate into the volumetric flask. Slowly fill the volumetric flask just to the line with water, again being careful not to overfill. Cover the top of the flask with parafilm and invert the solution several times to ensure that it is well mixed. Now we are ready to start making the measurements. For this reaction, a graphite rod is used. The graphite rod is connected to the reference electrode through the voltmeter. Once both the graphite and reference electrode are submerged in the reaction beaker, we have a complete circuit where electrons can be exchanged between the cathode and anode, or oxidation and reduction reactions. Carefully pipette the first portion of the dilute iron 2 solution into the reaction beaker. Make sure the reaction beaker is well mixed and record the millivolt reading. This is repeated for several more additions of the dilute iron 2 solution, followed by several additions of the stock iron 2 solution. Remember to mix the reaction beaker and record the millivolt reading with each addition. Once 10 readings have been made, we will be ready to move on to part 2 of the lab. In part 2, we will test if the potential of an electrochemical cell can be predicted based on the potential of the two half reactions relative to a common reference reaction. For this part, we will be pairing our iron half reaction with the iodine half reaction. Here we have two reaction beakers, one for the iron system and one for the iodine. With the graphite rod, once again, record the millivolt reading for the iron half reaction against the reference electrode. With a second graphite rod, record the millivolt reading for the iodine half reaction against the reference electrode. Now, we will disconnect the alligator clips for the voltmeter from the reference electrode. Consider what you think will happen when the iron and iodine half reactions are combined into a new electrochemical cell. To complete the circuit between the two half reactions, we need to place a salt bridge between the reaction beakers. This string that has been soaked in potassium nitrate will serve as the salt bridge by submerging one end of the string in the iron reaction beaker and the other end in the iodine reaction beaker. Once the salt bridge is in place, connect the two graphite rods to the voltmeter and record the millivolt reading. Finally, swap the red and black alligator clips of the voltmeter and once again record the millivolt reading.